So what I did is when I went through, there's about 7 sections in total. So we have diffusion, stress-strain relations, so various ways to look at stress-strain. Something called critical resolved shear stress, atomic radius and lattice parameter, that kind of relates to your Miller indices, but it's kind of its own operation by itself. Bragg diffraction. I did its own section on Miller indices because there were 2 or 3 questions I saw. And then 7th section is other, but there's really only 2. There's only really, well, I say 2, but tetrahedral and octahedral didn't really fit into the other subject matter for you. And actually, 7.2 is all, these are all conceptual questions that I found on previous review materials, so I put them all here. I was told you could find most of these in your book, so I'll give you a chance to look at these at the end, at the section, but as a hard copy, I was told that you should be able to find most of those answers in the book if they were find a picture or something, so we'll start. And diffusion. So here are your 2 major diffusion equations you're going to be using. You could do probably 5 or 6 different variations because of the number of variables you have. So you have diffusion equals a diffusion constant, d naught. And d naught is going to be variable depending on what type of situation you're in. So I've noticed that like they're going to give you always need 2 components usually, right? You always need 2 elements that are going to diffuse into each other. So you're usually going to be either given d naught or if you don't know d naught, I think is one of these examples, then it's going to be the same for your 2 materials no matter what. It's going to be the constant in all your situations. So here I listed all the variables. We have diffusion constant, your activation energy, your R. This is usually given in joules, which should be a big J per mole. T is in your absolute temperature. So what does that mean? Anybody want to? Kelvin, thank you. Yeah. So remember, absolute temperature is in Kelvin. So hopefully they don't give you degrees Fahrenheit, because that would just be more calculations for you on a very short term test. Is it a 1 class or 15 minutes? Okay. And then we jump to our second equation here, which is your diffusion distance. When I was looking up diffusion distance for you all, even though this is, if you know matrices, this is not a matrix. This is meant to be you have a choice. So depending on whether or not you're going to be considering 1-dimension, 2-dimension, or 3-dimension diffusion, you're going to pick a constant to plug in here. So if I'm only in, I think I only noticed the 2-dimension diffusion, you're going to pick 4. And your equation then becomes 4 times d times t. So it's not, there's no matrix multiplication, if some of you know about that. It's just pick a constant and then dt. You're gonna, I believe we only are gonna, I don't know what you went in through class, but 2D is probably the most reasonable to use. Or if they say 1D, just make sure you realize there could be a difference that later on. But you simply take the square root, and you're gonna say, if you take the square root of 4, you get a 2 dt, and otherwise you get a square root of 2 or square root of 6 dt. And remember, d is this whole entire expression that you might actually have to calculate. So, any questions on those equations? Yes.
0 is always positive, right? Otherwise, this would be complex number. Your x would not be negative.
Right. Have you ever come across that before?
I'm just saying.
No. Yeah, d will always be a positive. Yep. Anything else that you ran into? This conception? So the first example, the diffusivity of copper and brass is 1 times 10 to the negative 20 meters per second at 400 degrees C. Approximately how long will it take copper to diffuse 0.1 meters through brass at this temperature? Well, you have 0.1 meters as your distance. diffusivity, copper, T. So we're looking for a time. So we're going to use our second equation because we know this is our D. So we got 0.1, what's our units? Meters, good. Equals, we take the square root, I'm going to use 2D, so this is 2, times the square root of, so we're looking for time, so 0.1 squared equals, I'm using 2D, 4 times this number, 1 times 10 to the negative 20th meters squared per second times your time. I always encourage you to check your units really quick just to make sure you're doing stuff right. So this needs to be in seconds, or if I was given it or if I'm finding it, this is in seconds, seconds cancel. This is in meters, meters squared equals meters squared. I'm good. So T is not too hard to find because we can move everything over to the left-hand side and solve for T. So now this is part 2 of the second. But using that data, what will be the diffusive copper and brass at 600 degrees C? Activation energy for diffusion. We need to calculate the activation temperature.
We had a question quick.
Sure.
How did you know, like, what about the question being that it was question?
I don't have experience or anything with it, but from one of the problems I was given, it was in 2D, and I figured it because I saw the answer. So what I'm going to say to you is, I think you would look back to your notes and figure out what was the most commonly used expression, or did your teacher or professor ever say we're going to stay in 2D, even though there are other dimensions we can go to. So I'm saying we're using 2D because I noticed that was actually used on an example. So that's why I brought it up. That's why I brought it up, all these numbers for you, as a reminder that you're not using this one. Does that answer your question? It's not, I don't have experience with what they're going to choose, but alright, I need to get mine. Okay. Okay. This one. Okay, so I'm a little confused just because I'm a little shaky on the terminology, but just remember, I would suggest looking up what the difference is between D and D naught and make sure you know what the terms are for each. Because if this is, if it's the diffusion constant or they say D naught, you're okay. If this just says diffusivity, you got to make sure they're talking about D or D naught. Because otherwise, in this one, I have to do an extra step to calculate the D. Okay. It's not too complicated. Just make sure you know what terms belong to which, but they don't get will be here. So at 1100 C, the diffusivity factor is that, and at it is that. Calculate that. Okay, so this is D, not D. Calculate the activation energy for diffusion. P is silicon, R equals 8.31, so we know that's in joules per mole. For this case, the homework solution is a little bit quicker than what you might think on an exam, but the key concept is that D naught does not change for these. So what they did is they took D equals D naught exponential a negative Q over your RT. And this is what doesn't change, because you're given D, and you're given R, and you're given T, and you're trying to find Q, but you don't know D, but you just know it's constant depending on the temperature change for the two different rates of diffusion. And so what you can do is, you can either solve this for D naught and equate the two, or you can divide everything and say, you know, D1, T1, so that relates to one of these two. Either this, or this is one, so let's say this is one. D2 equals D naught, yes, Q over RT. On an exam, you can show if you're looking for an answer, there are shortcuts. So in this case, they wanted you to find activation energy. However, you know that D naught is not going to change depending on the diffusion change and the temperature change. So you can either solve for D naught and then equate the two and then rearrange everything to find Q on its own, or you can do a fraction, a ratio, and notice that the D naughts cancel, and you can then solve in terms of Q. To do that, you would simply take the natural log of both sides. So this, because this is negative, I can move this up to the top, and I can do that as a fraction. So I have natural log of D1 over D2, whichever one you want to choose. Make sure the temperature is correct. Your D naught cancel. This is going to be D to the exponential, or sorry, natural log. Natural log of D to the, these two terms are multiplied to each other if I move this one to the top. So I really get negative Q. I can bring out a negative 2 times. Can you see that? I can bring out a negative Q on top. That's going to be 1 over RT1. And because this is actually positive up top, this is going to be negative 1 over RT2. This goes away, leaving you with just negative Q times that expression, the natural log of D1 over D2. And then you can solve for Q. Any questions on that? So you know how exponentials work with each other. You know natural log exponentials. Okay. There is a sheet that should be going around. If you could put your name and your A number on it too, please, for the arts record. Okay, so our next example deals with diffusion depth, which is the same thing as the distance, how far into your material you're going to diffuse. Here they give it into millimeters, so we just got to be careful. The negative third. They want it done in 8 hours, so because this is in seconds, you either convert D naught into meters squared over hours, or you convert hours into seconds. And they give you Q, so you need to figure out D. So we have, this is the square root, so if we do 2D, which seems to be what we were given, what temperature? So we have D times the time. So yeah, I gotta convert. So 8 hours. Hour. 60. 3600. That'll give you seconds. If I square this, divided by 4t, square the 2, is the same, I get D. So there's my D. This needs to equal D naught, which we're given here. Exponential negative Q over RT. I'm going to add the 273 because we were given it. So that T is in Kelvin. So you would probably get a point or two off right, because if you just gave it in Kelvin, you technically were not answering the professor, or if you were in like industrial world, you weren't giving it to somebody in terms of chemicals they know. So if they've done Celsius ultraviolets, and they know how materials work in Celsius, and you tell them Kelvin, well, they should be smart enough to convert it. But if you have a whole chart in Kelvin and you need it in degrees Celsius, you better convert it. So just make sure you answer the question correctly. So this constant equals all that, equals division and natural logs, we're all set. So that was one of the major topics I saw on the review. There were probably, I put 3 of them there, but you could rearrange stuff, So topic 2, I did not add any stress-strain relations. I will send it, when's your test, Thursday? Okay. I got these from a study guide that I was given. So I will attempt to put up some of those questions or give them to the art center so that maybe you guys can get your hands on some examples. But if you want to look at what overall was happening, we have what we call, I know it as engineering stress and true stress strain. You might have been called nominal, which is what the N is for your stress and strain here. That's also engineering stress strain, but that's not the same as your true stress, true strain. These are the basic definitions whenever you run a tensile test. You have the force over your area naught that you began with. It's going to be your engineering stress throughout the entire procedure. And then your changing length over the original length is that definition. When you convert it, this A is not A naught. That A is technically the area if you're talking about true stress, it's the area at which that force took place. So whatever elongation you are at, usually it occurs after necking. It always occurs after necking. Whatever the area was after necking occurs, that is the actual area that would be decided upon for your true stress. So usually you'd be given that information. You don't really have to figure it out unless you were given like a radial distance. You said, at the time of this force, the radial distance is this. Please figure out the area. That's really true. The more important thing, though, is for true strain, there is a way to convert it from your nominal or engineering strain, which is the bar equation to the right there. And then the true definition is your length final over your length dimensional overlap. Did you want me to prove how to go from one step to the other? So you feel safe with that? Or okay? Is that better? Okay. Sometimes you'll be given what's called a yield stress, and that's just a reminder. Yield stress is at the point at which elastic transfer happens to plastic. That's usually considered at the 0.2% strain. So if they say the yield point, that's not your ultimate stress. It's actually just the definition of what occurs or how far material can be stretched before you would consider it to be plastically deformed. So up until that point, it's elastic. However, that yield stress is important. I think in like, I'm not sure how many equations in your book. I think there's like 2 that I ran across, 2 or 3, that dealt with the Berger's vector, atomic distance, and your shear stress. And given those, you were able to figure out one over the other. I'm not sure if you were told, but there are ways to calculate the magnitude of the Berger's vector. And I think the easiest calculation for your test is simply, what I thought I saw was just 2 times the atomic radius from what I saw. So don't quote me on that, but please look that up and see what happens to that. Because I know there was some more complicated stuff that could go on with the calculation of that magnitude. But from what I saw, maybe you'll be given like 13, 14 questions, kind of similar to what I did up there, and you should be able to kind of just 5 minutes each one, if you know what you're doing, right? If things run smoothly, and there's nothing new or challenging that unit-wise or something. So there won't be any massive calculations that should be taken like half a page or a page. It should be like a third of a page or something, depending on how big your writing is. So the third section I saw was called the critical resolved shear stress. This kind of ties into 2, but there were a lot of questions on this, so I developed an own section for it. Is that better to see? So you have tau of C is your shear stress, but critical, equals the yield stress times these cosine of these angles. I listed the angles for you. It's the angle between tensile axis and slip plane, and the angle between tensile axis and slip direction. Coming back to this, I was a little confused why the angles were not the same. And I looked up a drawing. So it's holding tension. And this is nice and easy because this is your slip plane. It's the plane at which this will slide. At which it's going to slide, and that's always going to be given to you. I mean, I don't think you're going to have to figure it out. They kind of just give you the vector, the Miller indices for a plane, which is nice. And we'll go through some examples. However, just because this is the slip direction. However, just because I happen to put the arrow in the direction of the slip plane does not mean it's always going to be in the same angular direction. Because what happened is your actual microstructure could be orientated so that, yes, this is the plane along which it slips, but it's actually going to slip, you know, coming out of the board a little bit, like that way first, or something. So it's actually going to slip along a different direction first, or maybe that's the easiest path of slip. So from our visual standpoint, it looks like it came off going that way. But if you were to look at the actual microstructure and like look at the texture, you would see probably like, if you were to look at a cross section, maybe you see all these lines going, and you know, this was the direction we thought it went, but all the cracks and all the breaks went in different directions. So there is a difference between the direction it's going to slip, which they give you as a Miller indice, either in the plane format or as a vector. So don't always assume they're the same, which that's going to be. I put this little blurb. The angles will be given to you, or you need to find them, or the cosine of them, because I noticed there were some shortcuts of the angle through the use of definition of the dot product. So if you use the dot product, the definition, and say you were given a vector in Miller indices and a plane, you could take the dot product of those two. Do the summation. And then this is simply the magnitude. So this section right here is the magnitude of that one. And that one, of course, is that magnitude. And then, of course, because of the definition, you get the cosine term. So therefore, you get a constant, and you can find out the whole term of cosine instead of having to find the angle first and then calculating the cosine of the angle, or if you need to find the angle. Because sometimes they're just going to, one of the examples is going to want you to find just that. And what's nice is you can just calculate just the cosine of your specific angle. You don't need to actually get that angle. My vision. Is that it? Okay, so this one is calculate the angles between the following in a cubic crystal: 111 and 121. So that uses the definition I just gave you. So you can say 111 dotted into 121. Equals, so 1 squared plus 1 squared plus 1 squared, 1 plus 4 plus 1. And then you have the cosine of your angle. Don't worry about what the angle is, but they just want an angle, so it's not slip direction or slip plane, or angle between slip direction or plane. So you do this out, you get 1, 2, 1, 4. Over this, that's 3 times 6, 18, so it's cosine. Take the inverse cosine and you get your angle. Do that 3 times. It doesn't matter if you're dealing with, in this case they don't trick you, like see there's 2 planes, 2 vectors, 2 planes. You can do it between a plane and a vector. There's a shortcut for you. And now we're just going to do the same thing. They give you a little bit more of a realistic situation, so they give you a copper crystal in the form of a thin cylinder. A thin cylinder allows you to when you with a thin cylinder allows you to negate any kind of other forces pulled in other directions. So you can say that I am directly pulling up in the direction of my my given vector. So they say, okay, we're pulling along the 1, 2, 3 direction. Well, it has its boundary conditions because it's so thin that you won't be pulling in some other vector. I mean, that's just kind of pinching information, but that's why they add this thin cylinder. So you don't need to overthink what I have to do with the thin cylinder. It's kind of a conceptual thing. The slip plane is 1 bar 1. You need to remember if there's a bar over it, what does that mean? That means it's negative. Okay, so if you have a bar over a number, it's negative. So that's 1, negative 1, 1. Slip direction is 1, 0, 1. That's a plane. This is vector yield strength. So what is tau? Not too bad. So tau c is going to equal 120. That's given. Now we need these two, right? Cosine of theta and cosine of lambda. Cosine lambda. However, we kind of just did that up here, or in my small example previously. So we just have to be careful to know which ones we take. So this is along the axis. So if I have a thin cylinder, that vector, however it's arranged, however my material is arranged, is going in that direction. However my lattice is designed. The actual pole is along the 1, 2, 3 direction. The slip plane is along that direction, so I quickly went through it, but one of these angles correlates to the slip direction with the angle between the tensile axis and the slip plane. So you got to use those two together. We'll just use those two, so we have 1, 2, 3 dotted into 1. Right, because this is the two magnitudes, remember. So that takes care of that cosine of that angle. So I didn't really need the angle. I just need to calculate the cosine of it. Good. So it gets pretty repetitive because we do the same exact thing with the slip direction and the axis. So we can put in another thing there. So I guess the key thing you don't want to do is you don't want to dot this one and this one together. Okay? You don't want to dot those two together because those are not including the tensile along the tensile axis. You don't want to dot those two together. Any questions so far? And all of them were they were like variations of that. Can I erase this? So my next section dealt with atomic radius and lattice parameter. So I summarized for you simple cubic. I summarized this for you, so if you need me to do the drawings of why this is true, I'm more than glad to do that for you. Does this ring a bell? Is this a good review? Okay. Do you remember why this is true, or do you just want to know it's true? Does anybody want to know why it's true? If you remember, that's fine. Okay. You don't remember? What? Okay. All right. Okay. No problem. Yes, it is. It's I believe if you go to the Art Center and look up to ms201 somehow, or find a link to it, it will say review. It will say review, like exam reviews, I think, is the first link. There should be a link for exam reviews, and then you should find ms201. I was told it was up. If it's not up, I apologize, but I was told it was up on the ARC website. IIT, ARC, ARC is all capital Art Center. So in an FFC, you have face-centered. Oh, shoot. You will not have me as a tutor. So if you like me so far, so in a face-centered, we have what's called your closest neighbor, or nearest neighbor, or close packing. Close packing, and because we have a face-centered, we have a particle equal. So we have one here, and then this one is going to touch those two. And this is for face-centered. And so your closest packing distance from the center of each atom is along this face right there. Okay. This is your lattice parameter, A, or A now. Yes. So that, like for that one, you don't want to, because one says tensile axis, the other one says slip direction or plane. You don't want the two. You don't want to get rid of the tensile axis. Right? You need that one. Okay. So for FFC, we have from here to here is R. I put it small r. So if you have 4 of those from the center, that actually is going to equate to the square root of 2 of A, because this is A right here, this is A, and this diagonal is going to be root A squared plus A squared equals 2A squared. Square root each side, I get square root of 2A. So that distance along the angle of that front face, because that is the closest, nearest neighbor, closest packing, is going to be square root of 2A. The other thing you have to remember is the number of atoms is 4, because each corner is 1/8. There are 8 corners, so you have 1. Each face center atom is going to have 1/2 of an atom. So unlike the corners, they're going to have 1/2 of an atom. So because it's being shared, because if you put those 2 boxes next to each other, that atom is split down the middle between 2 simple lattices, simple structures. That's why you get 1/2 on the faces. So because there are 6 1/2s, 6 times 1/2 is 3, 3 plus 1 is 4. So therefore you have 4 total atoms in the lattice group of 6. So the same thing goes with a BCC, except, however, instead of having it along the face, we now have that one atom in the center of our simple lattice, simple cubic lattice. Try. So now you have this as a three-dimensional atom going in the lattice structure. And we're actually going from this corner to this corner by 4 radius. Hence, when you calculate the length of that, it's going to be square root of 3. It's the same idea, you do, write it, you do hypotenuse, a squared plus b squared equals c squared twice. Another key thing to remember for your notes is AMU is actually grams per mole. It's a simple conversion to grams per mole. Another thing to remember is just density is mass divided by volume. Except in this case, we take the assumption that volume is going to be a cubed because we're dealing with simple lattices. So even though there's going to be some space in there because the atoms are not fully filling the lattice, the assumption is that we're taking. Do you need me to make this bigger somehow? Okay. Volume is going to be your lattice parameter a cubed. And then I equate down at the bottom there for you, your mass is going to equal number of atoms. So therefore, that's why you need to know what structure you're dealing with, FCC, BCC, or even. Okay. Okay. No problem. I was given two review materials, so I condensed it all into one. Does some people need a review on it? Like fracture fraction on your last test? Yeah. How about everything so far has been on your last test?
No, that's the last one.
Okay. I don't want to waste your time. Miller indices is also on your last? No? Yeah. Okay, can you guys do this real quick? Sketch 6 cubic unit cells with this planes in these directions? That was the question, okay. And you can calculate using the lattice parameter, and you can know where you need to go inside your, basically this question. Yes? Okay. Take a look at these conceptual questions and see which ones fit in for this test. Yeah, please take a look at these. There's like several questions here. I'm not sure which ones, but these are good, I think, anyway, because you don't know what you're going to be reading, I guess. All of these? All of them are relevant? Well. So we said that was good. So we said up to 4. We knew 4, right? So 1, 2, and 3 are all new. Okay. So like here, I already have 3 questions for section 1. You could probably add 2 more or 3 more if the professor was desperate, or that so you're not copying these word for word and like you know how to do them already. I mean, they can change things around, they can vary things, right? But they're not going to vary too much more than what the professor gave you already, because I think these are also review sheets. Did the professor give you a review sheet? Okay. So it'd probably be good to look these up on the ARC website. No one can find it?
There's one semester posted on there.
Yeah, that's not it. I know that one. That is not it. Let's see where he put it. Just out of curiosity, did the professor tell you how many questions was going to be on the exam? So I gave you about like 6. Plus, there's like a ton of conceptual questions. Where was this? So that's that one. So I grabbed some questions from here, but this looks like the old one. Was tetrahedral, octahedral, was that anything old, new? That was last exam? Are there any questions on stuff that you feel would be on the exam but I haven't covered? Yeah. Figs first law. Yeah, I think that's this is the differential form of it. And so if you I think x squared equals that number minus bc is a variation of this. I think it's a variation. Yeah, so I think the true definition is up there on the screen, but once you do the actual practical and getting some manipulation, you get time. Any other subject matter I can look up for you and answer? I'm going to just scroll down to the bottom here for the conceptual questions if you want to write some of those down. What time did you? Yeah. So. Well, for during deformation, if it's like a tensile test, you have your stress, which is your force over the area, and then you have some elongation that goes with it. If you're in the elastic regime, you don't need to worry about the change in the area, right? Because no necking occurs yet. And so you can use the fairly simple, the definition of work, right? The force times dot of your area. So it's in the direction of the direction of your distance, which your distance would be the elongation, right? How much it changes. So maybe you're given stress, and you have to find force, and then you can do force times distance.
Discuss that free strain versus stuff.
Yeah, I can do that.
And it's just, yeah.
Switching, like all that. So I had a question about creep. What's the question again?
Stitch, spring versus time, strain versus stress.
Strain versus stress, or stress versus strain.
Strain versus
So, if you're doing engineering stress strain, you're going to have linear for your elastic region, and then it starts to plastically deform up to a maximum where necking starts to occur, and then it's actually going to come back down and then break. That's usually what a curve looks like.
this is stress versus strain.
This is
Let's know the stress strain curve.
So this is metal. A polymer, I don't remember the exact curve, but it should be in your book because that's something most textbooks show quite clearly. They're like, okay, this is a polymer, this is a metal, and they're going to be completely different. So there's no need to like guess. You'll know which one's different. I could probably just
stress versus strain.
yeah. This is the nominal or engineering.
Okay, so go to right of that.
So what do you think? What do you think would go here? Sigma. I'm going to put engineering or nominal, however it was taught, and then this is going to be your strength.
And the point,
Use your words right here. This the top of the curve.
so
That would be where necking occurs, and that I think it was given to you as the ultimate stress port, because ultimate meaning it reached its maximum stress value.
sorry, just look at it wrong.
Ultimate tensile stress. So if you were asked another variation, which you could be asked, is the difference between this and true strain for tensile tests. And true strain actually will continue to grow. Engineering stress will come down to a point of fracture, and if you're going to graph true strain versus true engineering, so this is now sigma true, that's going to increase. Are there any other topics that you think that I didn't cover that can be helpful to you? Do you need me to go back over some of the stuff we talked about?
can go from hard to hard to
Do you have? There's several. Which ones were you taught?
There's a.
So I think the one question, I don't know if you guys would have any calculations with those, but the thing to remember is the head of the shape head, what type of formation it makes. I can't remember, but there's your very basic one is a round one that goes into an indent, and then you have a diamond shape, so this is the surface. So it's not really a diamond, but it's more like it is a diamond. It's elongated in one direction and the other. It makes a indent like that. Makes an indent. There's a special angle associated with it. I think it's 100 and is it 30 something? 36. Vickers, I think.
This is Vickers.
One of the two is very similar. I think the angles change. Or the shape is slightly
like
different.
the version of that. It's have any coloration.
Which one? There's like a dozen here. I'm just saying they're not two separate questions. They're like there's many questions within the paragraph. So it's only six. I didn't realize half my material would be. Well, I haven't done creep strain versus length. Anyone know what that is? Creep. Creep. Did we talk about the creep? Is that something that they talked about?
You just mentioned.
Just mentioned it?
That's a problem.
Well, I'll go. So, creep deals with a constant load. So, unlike a it deals with a constant load. So in a creep diagram, you have three sections. Usually the most important are the first two. And this is time. So over a very short amount of time, when you have a constant load on a material, it's going to quickly jump up to a certain strain value. Actually, this is wrong. This is chalk. Where did I go? It's actually going to jump up to a quick strain. Creep. I heard it was mentioned, but it's really not. I don't. I'll look into it. Classic deformation. I mean, was it unclear how to do it, or was it just the equations didn't make sense? Do you have equations for me?
That's pretty much equation. He said it could be 1D, 2D, or 3D. Number changing. 4, 6, but he just said 2D. Whatever you did. Or, okay. He just talked about this. Yeah, but this, and then she's gonna say, like half the class was missing after a quiz. Yeah, he said, I'm gonna give this for sure. Don't tell anybody else. I know how he is. Don't tell, but this, which is the fundamental concept, I mean, this depends. This is not. He said, it's a good question. But I asked him, which one is the fundamental concept? This is not understand. This is. He said,
I'm stressing it.
this is plus shear. This is the shear.
So the
Shear stress.
the yield stress depends on the center.
That, yeah, that's a fundamental. The yield stress depends on the shear. The shear does not depend on anything. Pretty much everything depends on it. He said,
I've had a question about work done during deformation, so I was asking to listen because I did not attempt anything on it. So work done during deformation that was given to you is the energy per unit volume equals the work done per unit volume, which is exactly this definition. The work done equals the stress times your actual your strain, your elongation. A unitless elongation. Okay, because this is strain, so the unitless elongation. However, what you can do is you can plug in that sigma equals E, your strain, your Young's modulus, because this is true up to the elastic portion. So during deformation, if you don't go past the elastic region, this will hold true for the fluid. That's simply plugging it in, and now you have a constant, a material constant. That's always going to be the material. Your material could change a little bit, hence your Young's modulus can change, but if you're holding your composition pretty much constant, the E is going to stay constant. And then you have this scenario. In calculus, you were able to do that, and you get the integral. You get 1/2 E strain squared because I have to add 1. So 1 plus 1 is 2. I have to go 1 over the new number, 1/2, and I get this as your work done. So what that's saying is, if you know how much deformation, how much elongation, unitless elongation is done. Now remember, if they give it to you in a percent, you cannot use the percent. Okay, you have to use the decimal, because the percent is something that is used for other scenarios, but you always have to use the decimal form of your strain. Yeah, I mean, I'm pretty sure you're given, but strain, you might have to do like some calculations, like, this would be, it doesn't matter because this is in the elastic region, and so we don't go, in the elastic region, the true and the nominal are the same. They don't change from each other until either one would work for that. Well, either one would work in that region. Actually, they should be. There should be very, very little change in the two. However, we're not past necking, and we're not. So you probably want to use the original, which is the change length over yeah. However, with your question of these, how does the shear strain work? How does shear strain work? It's the exact same thing. The definition of the shear modulus is I'm not sure what, can't remember what they used for. So your shear stress is tau now, and your shear modulus is G, and your shear strain is gamma. Okay, so tensile is when you pull two things apart, and shear is when we're shearing, so we're putting a force parallel and opposite along two different directions. So that's why you get different terms. But the math works out the same because this is similar to this. There's no squares, there's no cube roots or anything. So therefore the work done is going to be the same if you're dealing with a shear situation. You can do 1/2 of G gamma squared, where this is the elongation due to shear stress. And you get your tau squared over G by plugging in using your linear section. What I mean by that is I want to get rid of say I only have stresses, they don't give me any elongation, unitless elongation. This holds true for the linear section. Right, and then it curls off. So this holds only for the linear section. So if I wanted to rewrite this in terms of only stresses, because G is a material constant, it's going to be the same if your composition's the same. I get 1/2. This is tau over G. So I get G tau squared over G squared. And that is what you have written in your notes. It's tau squared over G. So maybe it was just a quick day. The professor was going quick, but they're using your linear equations there. Re-plugging in, re-substituting. So sometimes we have to rewrite our equations because some things in terms of the lab, some things we just can't, are easier to measure. So it might be easier to measure the stresses. Okay, well I can write my equation in terms of stresses too. So I don't just need to figure out my unitless elongation. Okay, so this goes back to your Miller indices. I got a question about kind of how to do a lattice. So do you think this is going to be on the next exam though?
Yeah.
Okay, as a reminder, your curly brackets, it gets kind of confusing, but your curly brackets indicate you can put basically put bars over your numbers in any arrangement. Okay, so if I have, in this case, 1, 1, 1, and this is for a plane, that means we're talking about this scenario, this plane. It's a long list. This plane. I think that plane. So it basically, if you can equate all the planes along a similar all your planes along a similar axis, or you don't want to. This is a way of listing more planes or more vectors, so you could add negative signs and stuff. So for this problem, it was just saying there's multiple slip planes, right? When you look at the lattice after all the data comes in, there's these slip planes, which equate to all of these. So you're actually drawing a bunch of different slip planes. However, so that's for planes, and I think for vectors, they use this notation for multiple, when you want to know more vectors. So list 3 specific slip directions that lie in a slip plane. So they give you a slip plane of 1, 1, 1. Okay, so where's my reference? So this is going to be my reference point that I'm going from. So if I go, if I'm given a Miller indices, you have to flip them, right? So if you're given 3, 3, 3, you're actually going 1/3, 1/3, 1/3. But in this case, they're 1, so it's nice and easy. So I'm going here, here, and here. However, I have a plane. So that's my plane. If I were to color it, that's the 1, 1, 1. This being my 0 point. Okay. It says list 3 specific slip directions that lie in the slip plane. 0, 1. Okay, you put 1, 0, 1, and that is not in the plane. You go 1. You don't go anywhere in the light, you go 1. So you said you want to go along this space. That's what you said. 1, 0, 1. You said I want to start from here, because that's my reference. And I want to go along this space up to this point. As you can kind of see, that's not in the plane at all. Right? That's not a slip direction in the plane. Okay? You also added you added these too. So maybe if this was correct and you added these, that could also be a reason why it's wrong. Maybe there's a included in this list a slip direction that's not true. That's kind of the you would need, actually, say that again. Yes. Does that make sense? So if I drew a vector, let's see if I can do that right. So if I drew this flip direction, along the bottom face, what would that be? That would be -1, 1, 0. If I dot that into my plane, I get -1, 1 times -1, plus 1 plus 0. Mathematics, graphical visual. Okay. Does that make more sense? Oh, sorry. This was my x, so -1. This was my y. And remember, you have to use the right-hand rule when you label your axes. So as I curl x into y, this becomes z. If I had y over here, and if I had x over here, this would not be positive z. So heads up. So you got to make sure that your axes do the right hand. This is my 0 point, but a vector, you can move the tail of a vector. Is the concept. So even though I'm starting here and I'm going -1, 1, and even though this is my 0 point, I can move this vector over to here and say I want to go -1, 1, and I can move the vector. So even though this is my reference point, and this is the positive x direction, and I'm starting here, you can move the tail of your vector. It's vector. It's the concepts of vectors. You can move the tail of the vector anywhere. So I can have it, 500 meters away, be something. I can take it up, pick it, move it somewhere else, and say, okay, that's the same exact vector. So this is the plane. You can visualize it. This is a 1-1 plane that comes cutting through the lattice, and you wanted this vector. You said that this vector is in the plane, which visually it's not. Visually, it's not in the plane. And then, what's your name? Nathan brought up the fact that, okay, mathematically, my dot product should be 0 because with dot products, if your two vectors are in the same direction, which this one is, and there's no angle between them. So even if I drew this one up to here, don't think of this angle right here. Don't think of that angle, because the actual angle is between the plane and the vector, which is still 0. So to make things easy, so I don't have to guess where that number is, we drew that vector in the plane. That's easy. And we did the dot product to show mathematically my vectors are in the same direction as each other. The plane vector and the actual vector direction are 0, and their angle is 0. So the cosine is 0. Right, cosine. Sine. Right, okay. I'm getting sorry, I was confusing you with the cross products and dot products. Yeah. 110 would be, according to my setup, would be from here, here, here. That would be the vector. That's not a split direction in the plane. Which you wrote down. But as you can see graphically, it's not a plane. Your other one was 0, 1, 1. So we don't go anywhere in the x, and we go 1 in the y, and so you went up to this corner, which again, visually, is And as a reminder, just be careful how you use your notation. Because your notation might add more vectors or planes. So yeah, that's another key thing. Because we're dealing with a plane, not a vector, the actual plane vector is normal to the plane. So if you want to think about it mathematically, I can pick a vector that makes my plane dot product equal to 0. I think it was good for me to draw it out for you. This is kind of hard the first time. You don't, unless you've had some kind of lattice drawings done for you. It's difficult. Any other concerns, questions?
I think there were two, yeah.
Good.
Yeah. Let me answer her question first. So that's your UTS. That's your UTS stress, and it wants the maximum force in terms of engineering. So therefore, you can use A naught because the stress equals force over A naught. And if I use UTS, that means this becomes the max force. Because since F is proportional to stress, if this is maximum, this is going to be maximum. Because this doesn't change. It's constant. If this increases, this increases. So this is using engineering stresses or the nominal stresses. So therefore, they gave you this and they gave you this. So they asked, okay, I want to know that. Does that make sense? So if this increases because this is constant. And then your question was find the. It has the curly brackets, so if you want me to put the plane. With the curly brackets, that means there's multiple planes, I think. Okay, so usually I choose that corner as my reference, my 0 point. And I'm going to treat this as x, this y, and z. So if I'm going in the 1, 0, 0, find the 1, 0, 0 plane in a lattice. So if I want to find, let me start. So which direction do I have to go first? 1. That's how far I want to go, but which direction? Which direction? Is this Z? Is this X? That's what I'm looking for. I'm going in the X direction, the first. So I'm going here, because that's the unit length. Unit 1. This is technically 1 over 1, 1 over 0, 1 over 0. Hence why these are infinity, why we get a plane. This is Y, and this is Z. So this is going actually 1 over 0, which is infinity. So it's going infinitely in the Y direction. So if I'm here, it's going to go infinitely. It's going to go infinitely in those directions. In the Y direction. Yeah, same with Z. And then in the Z, it's going to go infinitely in that direction. So actually, my plane is the front face of my.
Negative 1, 1. What was our negative? So 1 bar, 1, 1.
Is that what you were asking? Okay, so please tell me what to do. I want to go in the negative X direction. So yeah, so I'm actually gonna, because I'm working with a plane, I'm actually gonna start here. So I'm going to go 1 in the negative X direction. Planes are a little different when you deal with negatives, because then we'll also use to move the plane over like you can. Okay, so now I want to go 1 in the Y. 1 in Z. So what this plane is really doing is cutting across there, and then cutting up to okay, so it's coming up to here, so it's kind of cutting there. Okay. What that is like, if I were to draw it into the lattice I drew. It is. Because remember, this is the positive direction. I went back here. Alright, I gotta think about this thing. I'm just gonna do the way like a vector, you can move a plane once you draw it, because it's going to be repetitive within the lattice. So if this is my reference point, I'm going to go back 1. I'm going to go forward 1, and I'm going to go up 1. So those are my points. So I believe it is this point. Oh, I see. So I go -1, I go 1, that's the point. Okay. And if you want to think about it, if I go 1 in the negative direction initially, that's where my point is going to be. And then I go 1 in the y, so this one moves here to the +1. And my z would move, of course, to the +1z. And then what I did is I shifted it back over to my lattice. Does that make sense? Okay. So it's a little confusing because I had to shift it back into my lattice, or to at least draw it into this lattice from this reference point.
I mean, he just said it's just going negative.
No, sorry. It's
How did I
actually
get these from? Good.
however,
We saw them for the phones.
the curvature is
That's what's good. We saw it for this.
that.
So it was this.
What is? What?
This and this.
So, like say that's my 0.2%. It actually will have some curvature to it. But what happens is I deform it here, rub it back down, and then it will elastically come back. And that's kind of more of a standard. It's like a standard. It's like it's guaranteed to elastically shrink back at the 0.2%. Usually, it's also with engineering. It's also a safety factor, I think, too, somehow in there. So even if it deforms slightly, if it were to deform past this, it's not plastically deformed, but we never equate a scenario where as soon as it crosses the boundary, we're in trouble. So technically,
You can divide it by 100.
shield strength, and it'll have to deform past.
That's right, it's 100.
But it not like this. That's what the channel is.
So you gotta take it to you gotta take it like eight at least. Because if it was like this, they want 100% qualified off. So that's better.
So inside of my theater, you know what there, you know the share of the share. Yeah. I'm not sure if you know it. There might be, yeah, there might be.
Yeah.
Yes, passed out.
Oh, yes. Oh, yeah. So the community is just by that. I think that's much better. Yeah, so this is great. Much better. I think it's
Yeah, of course.
Noon is important. Like you really buy a killer, or you always buy a gun. Or you know you don't buy a gun. You're like 85 kills. 35? 35 kills. Hey, that's it. Hey, you good, man. You got a lot of kills, man. Hey, you do them, man. You're doing better than most of the time you're good. You're okay. What's the library for?
Because this is what that this is the issue. Because this is the plane that did I do this before? This one. Where's your breath? that one would be this one. Because with it, yeah. With that one, I don't think this one. That's the one that should and that would be good. This one. I think you move that. Yeah, because remember the plane vector coming out. So, but I try to make it easier by graphically showing if I draw a vector in the plane, and then without problem. So, like you just did, it's probably easier to do it along the face of the diagonal for that. Test is Wednesday or Thursday. I do. I should have. I should. I think I put both.
Is that it right there? What was it?
Are you ready?
I can try to figure out this one.
Yeah.
I kind of guessed this one.
Yeah.
I kind of guessed this.
Yeah, I got it. I did not get it right.
I think that was this one.
The other one's first.
Yeah. Yes, that's good.
Are you doing materials? What do you think? Oh, no, I'm like, I find material science like just the most boring shit that I ever studied. Like, I hate it.
Like, there was one guy, like, I was telling him, he's like, what the hell are you doing with that, dude?
That's the science elective that doesn't have a lab,
Yeah.
you know, so I was like, oh, why not? You know, I need one more.
Like, this, I thought that he was not, like, mechanical or aerospace, because he's actually, like, word because, like, kilogram, he's like kilogram dudes on it. Like, you know, like,
Yeah, I know.
What's your major, man? Like, it was,
Yeah.
So, like, what the hell are you doing here, man? Like, nigga got take this crap?
Yeah, I know.
That sucks, man.
I wish that, well, I mean, I guess I'd say that I took it because it's better than having to take it. You know, there's a lot of extra work in a elective.
A lot of it.
Yeah.
But it's okay, like,
I think I gave it to you.
you sent out an email or something.
Well, what I was gonna do is, since I don't know how long it takes, it shouldn't take long for something to be posted, but he has access to your ID numbers because of that, so he can look up who was here, and then I think it should be that hard for him to like go email listing and shove it off to everybody. That way you guys can get it. Because this is through the ARC Center, so the director of the ARC Center will be able to send out an email to the people who come through.
So, I want to ask a question.
Yeah.
So, I'm sorry, we go over that again.
Okay, so like for the first sentence, it's making concept. It's just saying there's multiple planes and multiple slip directions. So he's saying, okay, there's many slip directions, or many slip planes, many slip directions, but I want to know slip directions in this plane. The one I'm looking for.
That's the point out there. I didn't, you know, when you think about it, that question was kind of easy. I didn't really read it like that. I didn't think of it like that. I was like, I didn't even think about it like that. Like, it was, like, this was going on, this one was
Okay.
So he wants a direction in here, right?
He wants the direction, slip direction in the plane.
Any direction.
So I took. Okay, so like, if I go along the bottom of the plane, that's in the plane. If I started here, you know my reference is here. So I'm going -1. It's like going backwards. It's never a tail of the vector.
I'm used to doing this, but you're going the opposite way. I'm used to going one way, you're going the opposite way.
So technically, is there another review session?
I think so. Okay. So,
7. I'll be out here.
oh,
No, it's almost like.
you're for another player? I want 7. Oh.
Okay, so let me see here. Okay. So this is my reference to draw the plane. This back corner here. Was to draw the plane.
You know what? I thought I get it. Because when you start, if that is your origin, if you got a negative edge, you go backwards.
Right. So I'm like, okay,
Yeah,
I can start here and go backwards.
Go backwards. You just go backwards.
But it's really drawing this vector
Right.
in terms of this scale,
I get it.
and then I can move it.
Back.
Okay, good.
So what is the second? So there's only be -1, 1, 0, right?
So here's one in the plane. You could probably do this one in the plane.
But that one would be a, what would that one be going diagonal to?
-1, 0, 1.
And you can flip them, right? I mean,
So this is me drawing my vector up towards the corner. So if I drew my vector down towards the corner, that would be,
0, 1, -1.
yeah, because I go down -1. Yeah, so 1, 0, -1. It's a new language, like math.
Now you did the thing with the crossbars. Check it, because if it's conservative, it's
And that's because it's kind of confusing because the definition of the plane vector is actually coming out of the plane. It's not in the plane. It's actually coming. Yeah, that's a little tricky for students first time. It's like we're defining a vector of something out of it.
okay.
okay.